Okay, let's start the class. So in the last class, we defined the integral around curve. Okay, and so there are several versions of the notations. Okay, so here's a curve. It is an orientation, and then you have a vector equation. You parameterize it. Okay, so this is it's a function of a t. Okay, it's in the space. Okay, then you have a vector field in this neighborhood of the curve. That's f. Okay. So the integral of c and f, this is called so unit vector and the ds. That's called the integral of the vector field along the curve. So at every point, there's a unit tangent vector there. So this is inner product, just inner product. So that just tells you f dot f is going to be the length of f times cosine theta, which is the angle between them. Okay. Then, of course, we cannot do this, computation. We have to change it. If there's a parameterization, then so you get this another simple notation, f, okay, and dot dr. Okay. If you want to put the details, let's use this notation, and then so from A to B, that's t from A to B. Okay. And that will be f. Okay. Now, actually, this part is just t and ds. Okay. The reason is the unit tangent vector is the unit tangent vector. Let's see why this is true. Right? The unit tangent vector is defined by is calculated using this formula, right? And ds is the length of the tangent vector, and dt. So that's the ds. So multiply this out, it cancel out, then you get okay. So that's the whole picture. Now, what happens if the same curve, if we go from here to here, and that's a c, and if we're coming back opposite direction, that'd be c. Let's call this c plus, this c minus. With orientation, this is the same curve, but with this orientation, and I want to tell you this is an important fact. Here's a good example. Okay, the integral of f along this. Okay, and that is going to be dot t ds is going to be negative of this. It's very similar to the integral like is abf of fx dx. If you change the interval, order of the interval, you get negative, right? Remember this. Okay, it's very similar. So why this is true? Okay, think about this. At every point, f is always there. It's never be changed. But the tangent vector, okay, because this one, if this tangent vector, I'm going to denote by t plus, okay, because in that direction. Then t minus, because if you go from the right to the left, it's the opposite direction. So t plus is going to be negative t minus. It's the opposite to each other. Okay, so this will be the t plus. That will be t minus. Okay, so that's why, because t plus equals negative t minus, that's why you have this identity. Okay. Okay, so this is an important observation. All right, so now we are consider a special vector field. If you have domain D and then have a vector field right here, But we assume that this vector field is a gradient of some function, okay? Okay, for some function, okay? The gradient function, it's not a, it's coming from a function, so it's a very special vector field, okay? So you have this point P, let's take an arbitrary point Q, okay? And then those are the level curves, right? Level surface or level curves. Right. So this is you can say f of q is going to be some number, f. This is a f of p. Okay. So along this level curve, there has same value. Okay. Then let's consider a curve C start from a point on this level curve to point Q in another level curve. Okay. So let's do some calculation. Okay, this is this will be the gradient of f dot dr. Okay. All right, what does that mean? This is r dr. Okay. Yeah, you evaluate this. So I'm going to take an arbitrary parameterization. Okay, t is from A to B. So let's do the calculation. This is going to be from A to B, gradient of f. Okay. Now, by the channel, okay, by the channel, we have, by the channel, we have the following. So the derivative of f, and when you differentiate, okay, now if you want to put in more details here, suppose you have two components, right? Okay, then what are you going to do? So the partial derivative of f, right? Then this one, right? Plus the partial derivative of this. Okay. And this is going to be just a unit product. Okay. So it's unit product, the gradient of the unit product. Okay. So here, I just save time. I don't want to put the details here. Okay. So this is unit product of two vectors. And that is the gradient of f. Okay. Okay. Then the unit product was this. Okay. And we know that this is simply written as r of t. And this is r prime of t. Okay. So we get this. Okay. It's very simple. So we calculate this. Then we go back. Okay. And this unit product is nothing but the derivative of this function. So one variable function right now. Okay, by the fundamental theorem in calculus. Okay, this is going to be just evaluate at the two endpoints. Okay, and that's going to be f r prime v f. Right. Now, what is r prime? Okay, let's go back to the picture. So I draw the picture again. So this is point P, that's point Q. This is a curve, okay? C. So this is nothing but this is a R prime B, which is Q. So this is just a Q minus F of P, okay? All right, so, so when you look at the final result, you see no sign of a this curve C. Maybe there's another curve C here, but doesn't matter. Okay, this is independent of the passes from P to Q. Okay, so that means you have another pass C prime, and you end up with the same result. Okay, so two passes, for any two passes, okay, you will get this. Okay, let's use gradient of F. Okay, it's the same. So actually, it turns out to be FQ minus FP. Okay, doesn't matter which path you choose. You only see that the difference of variable function create a point. Okay, that's very surprising. So in the future, if you see this is the gradient of the function, if I ask you to find to evaluate the so-called line integral, some given path, that path is a very strange path, and you can solve that problem using let's see what we can have. I'm going to give an example. Okay. Okay. So here's a question. Okay. So I have fx. It's going to be it's going to be x squared plus y squared. So now the gradient of f is going to be 2x 2y. Okay. So the curve C is a very strange curve. So here's a point. Okay. So I ask you so this is a curve C. This is a x axis, y axis. Okay. So what I'm going to do is curve C consists of these 2 points. Okay, it's 1 and a 1. Okay, here's a 0 and a 2, 0 and a 0. Okay, this is a curve C. Okay, curve C consists of a line segment from this point to 1 and a 1, then to 0 and a 2. Okay. So if I ask you to evaluate the integral of C, okay, that'd be 2x and dx plus 2y dy. Okay. Now you should check whether this is So if I don't give the f directly, I just give that. Now if you realize that this is nothing but gradient of f times TDS, or this is a gradient of f r and dot dr. Then you don't need to waste time to you don't need to waste time to find the parameterization, then to evaluate. Okay, that's the usual way. Okay, so you can so look at this, right? So this notation, okay, and actually, let me check. Okay, so if you have this, right, so we can sometime the gradient of f is going to be partial derivative of x, right? Partial derivative y with respect to y, right? Evaluate at r, and this is a d. This one di is actually dx dy. You can also write in this form. So that means partial derivative of x dx plus partial derivative of y with respect to y dy. Okay, that's another notation. Okay. And yeah, I can even put the more, I can put the details here as the X and the Y and the X and the Y. Okay, this will be X and the Y here, coefficient, the variables. Okay, so if the line integral inside can be written in the form like that, then this is just equal to the value of the two endpoints. Okay, and Q minus F of P. Okay, now our point, what is point P? What is point Q? This is starting point, this is the end point. Okay, so all I have to do is just evaluate as a point, right? And the Q is 0, 2, so 0 squared plus 2 squared, okay? Minus 0 squared plus 0 squared, so it's 4. Okay, as long as you can recognize this is this vector field is a gradient of some function, then you don't need to waste time to evaluate integral. Just take the difference of the values of two endpoints. Okay. Okay. Another example we can do is, and the vector field x, y, z is going to be x, y, z. Okay. So it's in the space. The C is going to be a curved semicircle, okay, from here to here in the YZ plane, okay? So our T can be written as 0, cosine T, sine T, okay? T is between 0 and pi, okay? So we want to evaluate this integral and the F dot dr. Okay, we can say that simple. Okay. Sometimes we put R here inside F. All right. So how do you evaluate this? Well, if you can do that directly, no problem. Okay, you can do this directly, and you get the value. Okay, but you can also find out if we can recognize this capital F is a gradient of some function, then you can solve the problem quickly. So this is a point 0, 1, 0. This is a point 0, negative 1, 0. Okay, that's my P. That's my Q. Okay. So since F is a gradient of some function, F is going to be half of x squared plus y squared, z squared. I can see that, okay? When you differentiate partial derivative, you get x and get y and get z. If you recognize this, then this is just going to be letter F and the Q minus P, the values of this two endpoints. So I can have, this is going to be 0 squared, 1 squared plus 0 squared minus 1/2, 0 squared plus negative 1 squared, and 0 squared. And then that cancels out. It's going to be 0. Okay. So that's very quick way. So when you give a problem, just pay attention. Now we're going to, later on, we're going to check that. Those are the easy vector fields. Easily you can find out, find the F, but not, now some vector field is more complicated to see that. Okay. But we are going to learn today how to check whether the vector field is the gradient of some function. All right. Now I'm going to introduce a notation. This is the kind of definition. Okay, so we have let me then I explain to you. Okay. A vector field F is said to be conservative. Right? A vector field on domain D. Okay, so conservative if what's his definition? Yeah, there are several definitions. I want to check which one is better. When we say conservative, means it is independent. The line integral is independent of the passive. Okay, that should be the original definition. Okay. Right. So let's give you this definition. Okay. So a conservative if the line integrals of this is independent of the passes. Okay. Independent of the passes in D. Okay. So that means it's a vector field. So that means if you take an arbitrary two passes, as long as they have the same point and ending point, okay, then use the domain D. Okay. Then this is always only depends on 2 points, P and Q. Okay. So that means the line integral, okay, is going to be some function that are not equal to F, right? So it depends on only depends on point P and Q. Okay. It's independent. Yeah. If this C1, C2, that's writing this term. Yeah. Right. So that means for any two passes with the same end starting point and ending point, that could be, yeah, we call it this is the definition. Okay, when you say vector field conservative means it's independent passes. Now, what is okay? So the important theorem says that, okay, the important theorem says that if you're given function, right, vector field, we want to check whether it's conservative. So suppose F is a vector field, okay, that is continuous. That means the components are continuous, okay? On D, okay. Now this is these are connected domain. It's not like a separate domain, okay? So we have to be careful about this. Connected domain, okay? D, okay. Yeah, so F is conservative if and only if F can be written in for some function, is gradient of some function. Okay. Okay, for some function F on D. Okay. All right, so in the book, it says that conservative means, how do you because of equivalence, okay? So you can use the second one as a definition, conservative. A function, a vector field conservative means it is gradient of some function, okay? Then, then you have this property. So it depends on how do you define it, because they're equivalent, okay? and that is a theorem. And so if a vector field, the line integral is independent of the lines passes, then you can construct the function f. So the key proof is, yeah. So here's a simple proof argument. Okay. Now if this, yeah, we can assume this is independent passes. Okay. So we, yeah, suppose that this is an independent of pass. Okay, in D. Okay. Then you can construct a function in the following way. So first of all, you fix a point. Okay. So first fix a point x, y. Okay. Then for an arbitrary point x and y, since the domain D is connected, so you can take a path C. Okay. Then I define f of x to be the integral, the line integral of D. Okay. From this fixed point to that point. Now it's well defined. Why? Because you already know it's independent passes. So there is at least one path, and doesn't matter which path you choose, you will get the same value. And this is the function you are looking for. Okay, this function is yeah, this is a function actually is a yeah, this function gives you the, yeah, we claim that f is the gradient of this function. Okay, and that's the key idea. Okay, so that's where how do you that's how do you construct it. So I'm not going to give the details of the proof because we're not going to. Yeah, but you understand how do we get to the function. Okay. Yeah. All right. So then you say, if I give a vector field, how can I check, yeah, whether this is conservative? Okay, given vector field, how do I check if it's it is yeah, conservative? Okay, so given a vector field, okay, f, it's a p and a q on a domain D. Okay, how to check, how to verify, right? How to check if f is conservative? Okay, that's the question. Well, let's find the necessary condition. Okay, so if f is greater than 100, right? Then what do you get? Then p should be equal to this, right? Q should be equal to this, right? Then you will see that the partial derivative of p with respect to y, that is going to be partial derivative of f with respect to x and y. Okay, and the partial derivative of q with respect to x is going to be partial derivative of f twice. But those two doesn't matter the order of the partial derivative, right? Partial x, partial y, and partial y, right? That should be the same. So, right, they're equal. So that means we must have, okay, this is a necessary condition for f, for the vector field to be conservative. Okay, if that's some function f, capital F is the gradient of some little function f, then it must be true. Okay, this is a necessary condition. This is a necessary condition for f being conservative. Okay, this is a necessary condition. So if the vector field component do not satisfy this condition, it's not never be a conservative. Okay, so we have a let f to be right to be xy minus y squared. Then x squared minus y squared. Let's take a look at this vector, right? This is our p, this is our q. So partial derivative with respect to p, with respect to y, it's going to be x minus 2y, right? So partial derivative of q with respect to x is going to be 2x, and clearly they're not equal, so they're not equal. Okay, so then you conclude that f is not conservative. Okay, you never have a function, little f, so the f is gradient of some function. Never be. Okay, so it's easy to check. It's necessary condition is very important. Okay, it's not. Okay, so if you integrate the function along the curve, then really depends on the location of the curve. Okay, even they have the same starting point, ending point, then different passes that will give you different values in general. Okay. Now, if I modify, okay, if I modify the function, I'm going to still keep this one first, right? Then I get half of x squared and minus 2xy. Okay. I modify this, the second one. This is my p, this is my q. Okay. So partial derivative with respect to p, with respect to y, is going to be x minus 2y. Okay. Now, how about the partial derivative of q with respect to x? I also get x minus 2y. Okay. So they're equal, right? So the question is, are we able to find this f? Think about, can we do that?
Can you repeat the question one more time?
Yeah, this is we just check, whether this just those two components satisfy this identity, right? They're equal. Okay, the question is, are there, the question is f conservative? Okay, namely is f equals gradient for some function f. Right? So we have to find out that. Okay. I think it's possible. How to do that? Okay, let's try. Okay. So that means you have to solve these two equations. Right, it's a gradient, right? X, this is oh no, x times y squared, not this. Yeah, it's the original component. This is y squared, and here's half of x squared minus 2xy. Okay, that's a p, that's q. Okay, let's solve. Yeah, let's solve this equation, the system equations. Right, it's possible. It's not. This is just necessary condition, right? Partial derivative p with respect to y equals partial derivative q with respect to x. We hope this condition, they equal. This is also sufficient for us to find the to show that f is gradient of some function. Okay. Now how do you solve this? Well, for use the first equation, let's fix y, okay? Then I integrate, okay? Integrate this integral from take an arbitrary point okay, dx. And that is the integral, okay. But if you don't want to use a fixed interval, just indefinite interval is good enough. But this is with respect to x. Okay, xy, y squared dx. All right, so y is a fixed. So the first one is antiderivative half of x squared y minus y squared x. Don't forget plus a constant. Okay, it's plus constant. So that means f xy when you integrate, right, is going to be something like that. But that depends on y. Okay, y is a fixed. The constant is not constant. Constant with respect. Y is constant, so it's a function of constant. Okay. Then you find the partial derivative with respect to y. I get half of x squared, and then it's 2yx, and then c prime y. Okay, and this should match with the second one. And we find out, yes, this is already here. So that implies c prime y should be equal to 0 because this is supposed to be, okay. So that implies c is constant. It's indeed a constant, nothing to do with x and y. So we find that the function fx is half of x squared y minus y squared x plus any constant. So you get a family of solutions. Okay, and then the vector field is just the gradient of f. Yeah, we check. Okay, now in the book it says that if on the simply connected domain, okay, so I have to talk about domains first. This is a domain, okay, it's connected, okay. This is also, if I delete a hole, this is also connected, okay. So this is a called connect. Yeah, make a hole there, delete the part. So this domain D is connected. Why it's connected? Any 2 points, there's always a path go from P to Q, maybe from here, okay? This is connected, okay? And of course, this is also connected. No holes inside, so of course it's connected. Okay. So this is also connected. So there's 2 types of connected domain set. Maybe there's a hole here, maybe there's more holes there, right? And yeah, I'll give you one more example why it's connected, okay? Okay, something like that, right? And then make a hole here, you know, okay? And there's tiny bit here, there are lots of holes here. Right, so this is a connector, okay? This is a connector. Why? Because for any point in this domain, you can always find a path going through this, going through the domain from one point to another point. Okay. So there are lots of holes there, but this is still connected domain. Okay. Now simply connected means, okay, this is still connected. So for an every 2 point here, you know, I can always, yeah, I put a point here, P, another point Q here, right, far away. I can go through from here, I can go through from here, you know. I can go like that, okay? So it's connected, right? There's always a path you can go through, okay? Simply connect means, okay, simply connected domains. If there's no hole, roughly speaking, okay? Now, a domain D is called a simply connected domain if it is connected if it is connected domain, first of all, okay, without holes. Okay, so yeah, without the holes. So that means you can always this means you can roughly speaking, if you take an average point, you choose a loop, and you can make the loop short and short. You can always get back. Okay, and if there's a hole there, you can make it. You cannot make it short because of it. If you go around the hole, okay. So this is not connected if there's a hole here, because that's why if no holes, you can always shrink the loop, okay, to the point. Okay, so it's easy to see whether it's kind of simply or not, right? When you're given a particular domain. Right. So the theorem says that. Here's a theorem. The theorem says that if you have a vector field, let F with P and the Q be a vector field on a simply connected domain D. Okay. Now we have to assume that the partial derivative is continuous. Okay, we have to assume that they have the first order partial derivative continuous. So suppose, otherwise you cannot talk about partial derivatives, right? So you have to first of all you have the partial derivative, but also assume that they're continuous. All right. So what happens sometimes? All right. So we suppose that PQ have continuous first order partial derivatives. Okay. Then this equation holds, then F is conservative. Then F equals greater than sum for some function. Okay, you can always solve the equation. Okay, and it's guaranteed, but you have to make sure the domain is simply connected. Okay, otherwise you have a trouble to find this function. we can look at the following example. Okay. Right, let's take a look at the example. Okay. F equals 3 plus 2xy, x squared minus 3y squared. Okay. Okay. This is on the whole R2, no restriction. So this is the whole plane is simply connected. Okay. Okay. So let's try to find this end, right? So this is a P, that's Q. Okay, the partial derivative P with respect to Y is going to be 2x. The partial derivative Q with respect to X is also 2x. So py equals qx. Okay, so then by the above theorem, f is conservative. Okay, so f is conservative. Okay, so let's find since the domains since the domains whole are 2, so we guarantee we're going to have a function. So let's try it again to find it. Okay, so we're going to solve this equation f equals gradient of f for f, right? Then you end up with these two equations, okay? And apply the same trick to find the derivative, okay? To find the f. So first of all, you integrate, yeah, you can fix y, right? So y is the and then, you know, this is the derivative of f with respect to x, right? You can integrate with respect to x. Okay, y is fixed. So what you get here is if you get fxy, right? And then here's a 3x, I think x squared y, and plus constant. The constant should depend on y, because for fixed y, you get a constant. For fixed y, because for the y changes, the constant changes. That's why it should be function for y. Then you differentiate f with respect to y. So you get x squared. Okay, then y prime. You see, right? But this should be equal to x squared minus 3y squared. It's given. So now this time c, y is not a constant. Okay, you have this. So this c, y is going to be negative y cubed plus another constant that's called k. It doesn't matter. You can ignore that. If you just only find the one, now you have to find the family root. So put it back. Your fxy equals 3x x squared y, and the minus y is cubed plus k, so you get family of solutions. So this f indeed is a, you know, the gradient of this f is a given vector field. Okay, so this is how do we find out. All right, now for the same function, right? For the same function, evaluate this integral, okay, where f is the function we already discussed. Okay, it's going to be 3 plus 2xy and x squared minus 3y squared. Okay, and c is a curve. Yeah, c is described by this parameterization. Okay, t is between 0 and pi. Now, if we evaluate this integral directly, I'm pretty sure it's very complicated. Okay, I'm pretty sure it's very complicated. I even don't want to explain this. Okay. So first of all, you note that, okay, f is greater than little f. Okay, and this f we already find out is 3x plus x squared y minus y cubed. Okay, right? So as long as you see this f is the f is going to be this capital F is conservative and can express it as a gradient of some function. Then you have a starting point, ending point. What is a starting point for C, right? P is going to be 0, okay, which is when T is 0. So this is going to be 0. It's 1, okay? And Q is going to be the value pi. The first point is still 0. Sine pi is 0. Second, cosine pi is -1, so negative e to the pi. Okay, so you have 2 points. Okay, why I need that? Because according to our theorem, this is right. This is the integral of gradient of f dr. So this is just nothing but fq minus fp. Okay, the value function of those 2 points and take a difference. And then it's easy to do that because when q, x is 0, 0 minus negative e to the pi q, and minus p, x is 0, 0 minus 1 q, because the y is 1. The y value is 1. So you simplify e to the 3 pi minus plus 1, yeah, plus. So that is the answer. It's very quick. So if the vector field is not conservative, if it cannot be expressed as a gradient of some function, and I'm not sure within given time, then you guys can finish the computation. You know, sometimes it's impossible to evaluate integral, right? Yeah, sometimes it's impossible to evaluate integral. We haven't studied, yeah, for vector field in 3-dimensional space, right? Can we determine whether this is a conservative or not? Okay. There's some exercise in 3-dimensional. Well, we probably just need to focus on 2-dimensional case. Yeah. Let's take a look at some examples in the book. Okay. From 12 to 18. Find the function such that f is greater than f. Use that to evaluate the integral. Okay. Yeah. Yeah, we only see the above example just tell you, you know, in dimension 2, if the vector field, how do you check it's conservative? Because it's conservative, it's equivalent to the statement f is a gradient of some function. Okay, those are 2 equivalent, but the 3-dimensional, we do not have the theorem to check whether this vector field is conservative. Okay, but does not mean we are not able to answer the question directly. So let's take a look at the problem number. Let's say problem number 14. Okay, so the function, the vector field is in 3-dimensional. It's 1 plus it's 2-dimensional as the xy plane, e to the xy plane, e to the x times y, and here is x squared e to the xyj. Okay. I want to check with this conservative before I spend time on it, right? P and Q. Okay. The partial derivative of P with respect to y. Okay, this is going to be use a product rule if you want. It's going to be x times e to the xy plus, okay, plus the partial derivative with respect to y, so you get x So it's not easy to get simplified. You have x, you get 2x, and then you have x squared y. Right? So now you also look at the partial derivative of q with respect to x. So you get 2x e to the xy plus, when you differentiate with respect to x, so you get x squared y e to the xy. And you compare both, you find out they're the same. Wow. So they're the same. So py equals qx. Okay, so by the theorem, it's conservative. Okay, so it's guaranteed. Yeah, by the theorem, f should be equal to greater than f. So for some, okay, for some f. So we have to find out. Okay, so we have to find out means we have to solve this equation. You see, this side is p and q, right? This is a right? So you have to solve this two partial differential equation. What is my p? This is going to be 1 plus xy e to the xy, right? This will be x squared x times y. Okay. Now, which equation I should start with? Okay. I think that the first one is more complicated than the second one. Okay, so I try not to use the first one. I pick up a second. So this time I'm going to fix x. Right. So this is the derivative with respect to y, right? But f depends on x and y. You just assume a fixed one. So f of x y is the integral of right. Okay, plus a constant, get familiar with. Okay. So it's going to be x squared e to the xy dy. Right, when you integrate, what is the entire derivative of this? The entire derivative of this is x e to the xy. Right? When you differentiate, you will get x squared. Differential with respect to y. And don't forget the plus constant, which depends on x. Okay, because you fix x. So every time you get the constant depends on x. Then you use that to plug into the first equation. So when you differentiate this, you will get e to the xy plus x y e to the xy plus c prime x. Right? Yeah. And this is going to be 1 plus xy e to the xy and plus c prime x. And this should be called 1 plus. Okay. So that means c prime is 0, c must be a constant. Okay, must be a constant. Yeah, c prime is 0, then must be constant. So I got a function, it's different from the above one, right? The above one even get the solution, the cx is not a trivial. But this time, c is a constant. So our function we get is a simple function, just x e to the xy plus constant. Okay, plus constant. Right, plus constant. So now, once you get this, okay, and what is the question? The question says that evaluate this integral, okay, where I is going to be, r with t is going to be cosine t plus here sine t, okay? T is between 0 and pi over 2. So our starting point is going to be 1, 0. The ending point is going to be 0 and 2, okay? So those are 2 points. That's all we need, okay? You don't need to use a traditional way to solve this line, to evaluate this line integral. Okay, you can use the gradient to find to evaluate integral. So this is right. It's just have to be the end point minus the value function at the starting point. Okay. Right. So our function is x times e to the xy. Okay. So so the first point x times e to the xy. The first point, this point is going to be x is 0, y equals 2, minus e to the xy, and here's x equals 1, y equals 0. Right. Right. The second point. So let's evaluate. That's a 0. Here's a 1, e to the 0. That's -1. Oops. Right. Yeah. Okay. So let's recall, even in any dimension space. Okay. Let's recall that our terminology. Okay. F. This could be the region in the 3-dimensional space. Okay. So this is let's call it R. Right. So F is conservative on R. Right. By definition. If and only if, okay, the line integral, okay, independent of passes, okay, and that is actually equivalent to saying that f is gradient of some function. Okay, this is a connected region or domain. Okay, so we're using this. Okay, then but in dimension 2, we can check whether f is a just look at the components of the f. You can tell whether this is conservative. Okay, but if f is have 3 components, we don't have such thing yet. Okay, it is more complicated, but there is a statement in the there's a statement in the exercise actually. Okay, so if f so if f has 3 components p, q, r, okay, then you will see that then if this one equals the gradient, right, ff, okay, okay, so that means fx, fy, fz. Then what you can say, okay, then you can actually p equals f of x, right, q equals f of y, I equals f of z. Then you will see that py is going to be fxy. That one, which is f of, what is this fyx? That's be qx. Okay, you can check that, right? Then p and z. That's fxz. That's fzx. That would be rz. Okay. And how about q? We already use a qx, so that's qz. Qz is fyz. That is going to be fzy. That is what? Okay. So you do have 3 necessary conditions at the same time. Let me double check. This is X, okay, Rx. Yeah, Rx. And that is a QZ equals RY. So it's harder to memorize it. So those are the necessary condition, okay? If you see, necessary means you maybe not able to go back, but if F is a gradient of some function, then that component satisfies those three equations, okay? So that's our statement, okay? And whether this is sufficient, we don't know yet, okay? We don't have any theorem to guarantee this is a sufficient, maybe later, okay? So let's take a look at the last example. We are given, F, okay? This is y square z plus 2 xz square I, and here 2xyzj plus xy square plus 2x square z and k, okay? So this is a vector field in three-dimensional space, okay? Try to solve this equation for F, okay? And you can check that satisfies above three equations, okay? If this is a P, that's a Q, that's R. Okay, you can verify that PQR satisfy this equation stuff. Okay, so it is easy to verify that PQR satisfies the above equation stuff. Okay, but does not mean it's guaranteed. No theorem guarantee you can show F is conservative. So let's try to find out such later. Okay, so we got, okay, y square z plus 2xz squared, right? Yeah, then Fy equals 2xyz. Fz equals xy squared plus 2x squared z. Now, which equation we should start with really does matter, okay? I can try, so I have to fix, okay? I have to fix two variables, okay? I have to fix two variables first. I can fix yz, okay? Then f xyz is going to be integral for fx dx, right? So I integrate. Now, which one? Okay, the first term is constant with respect to x, so it's y squared z and x. The second one is x squared z squared, and then this time plus constant y and z. Okay, so this is a let's see, depends on yz. Okay, when you the partial the antiderivative is it. So we plug into the second equation. Yfy, I get 2y zx and 0, okay, and the cy, okay. Then I plug it. This is supposed to be 2xyz, okay. Then I plug into the third equation. I get the y squared x and 2x squared z and the cz. That should be x y squared plus 2x squared z. Not too bad. So I compare both sides. Cy should be 0. Cz should be also 0. So that means Cyz is going to be constant. Okay. So finally, I got the function f, which is y squared zx and x squared z squared. Okay. It's constant. Yeah. So plus any constant. Okay, so we find this there. Done. Okay. Now, here's Justin's question, right? Py equals qx is the 2D vector field guaranteed to be conservative. Yes, that was a theorem said. But we don't have a theorem in this section, it's guaranteed if above 3 equations, equation star, right? Above those 3 equations, satisfied guarantee. And I'm pretty sure this is true, but we're not going to spend time to get to later on, okay? In the late section, maybe we're going to talk about this later, okay? But at least we can, I think in section 16.5, we're coming back to this, okay? 6.5, we're coming back to this, okay? But now, yeah, for this example, we do have we can find this, we can show that this vector field is a conservative. Yeah, we do have a theorem for the 2-dimension case. The D must be simply connected. That's the whole point, okay? D must be simply connected. Then it's guaranteed. This is theorem thing, okay? It's a vector field on a simply connected domain. If it's not simply connected domain, I think we have examples. You're not able to show this is there is a function you can solve for f, okay? This only become a necessary condition, but not sufficient. This equation is only necessary condition, not sufficient. Yeah, I should give example here. It's not easy to construct such example, but we do have examples. Okay. Yeah, so like a domain like that. This is not a simply connect. Not simply connect. Okay, and I can construct a vector field. PQ satisfies those 2 equations, but you're never able to find F. Okay, little f. You cannot, it's not conservative. I can discuss this example in the next class. Right, so see you Wednesday. So we're gonna have a quiz.